بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. مرحب بكم بالجزء الثاني من المحاضرة الثالثة Lecture 3 Part 2. Now we will talk about inhibitors of adenosine deaminase. Alright. So what adenosine deaminase do? Okay. It catalyzes the deamination of adenosine to inosine. Okay. This is adenosine. By the action of the enzyme adenosine deaminase, the adenosine will be converted to inosine. This is the inosine. The difference is that the adenosine has amine group here, the inosine has a carbonyl. All right. And in the previous part, we talked about the reductase enzyme, right? And we talked about the inhibitors of the reductase enzyme. They found that increasing the level of the adenosine triphosphate in the cell will lead to the inhibition of the ribonucleotide reductase. Why? Because the deoxy ATP, this one, is considered as an allosteric inhibitor for the ribonucleotide reductase. So it is not going to act at the active site of the ribonucleotide reductase, but it is going to act as at an allosteric site. Okay? So if we inhibit the adenosine deaminase, that will lead to increase of the concentration of the deoxy adenosine triphosphate in the cell, which will eventually inhibit the ribonucleotide reductase, and that will inhibit or stop the synthesis of DNA, because we need the ribonucleotide reductase to make the deoxyribonucleotides from the ribonucleotide. Okay? Inhibitors, well, before we go to the inhibitors, let us have a look at the mechanism of action for the enzyme. Well, first, when the enzyme comes in, it has, as you know, there are some basic amino acids, right? So the base will abstract a hydrogen or a proton from water, which is in the medium. This will leave the charge on the oxygen. This charge will attack this carbon, which is partially positive. That will open up this bond to abstract a proton from the base again on the enzyme, because this enzyme is the same as this one. This is just one enzyme, not two different molecules of the enzyme. This is the same molecule of the enzyme, and that will regenerate the base again. Then the base comes back in, abstract this hydrogen from the hydroxyl group. This will form a double bond, and that will kick out at the same time. The nitrogen will abstract the hydrogen from the base, this hydrogen, and that will regenerate the base, and which will regenerate the enzyme. Loss of ammonia will form the inosine from the tetrahedral intermediate. Where's the tetrahedral part? This is the tetrahedral part. Okay? The inhibitors for the adenosine deaminase are a transition state isoster. Okay? Examples is the pentostatin, which is a natural product. It's not synthetic, it's a natural product. The pentostatin, it acts as a transition state inhibitor. Why transition state? Because this group of the enzyme mimics the tetrahedral intermediate of the substrate. And the tetrahedral only forms as a transition state between the reactant, which is the adenosine, and the product, which is the NOC. That is why we call this a transition state inhibitor or a transition state isostate, because it resembles the tetrahedral intermediate at the transition state. Okay? All right. Another enzyme is the DNA polymerase, and the inhibitors of DNA polymerases have been used as an anti-cancer medication. DNA polymerases, as the name implies, they catalyzes the synthesis of DNA. Example of an inhibitor is cytarabine, which is an analog of the 2'-deoxycytidine. The only difference between cytarabine and cytidine is that cytidine has the ribose sugar, the cytarabine has the arabinose sugar. And I think from your previous study, from your previous biochemistry, you know the difference between arabinose and ribose. Anyway, cytarabine acts as a product. Okay, it is going to be phosphorylated in cells to the corresponding triphosphate. Okay? The triphosphate cytarabine will act as a competitive inhibitor for the enzyme DNA polymerase. Okay, it can also act as a substrate for DNA polymerase. Okay, which means if cytarabine could not inhibit the enzyme, it is going to be incorporated into the DNA. And if it is incorporated into the DNA, it might form a non-functional or unfunctional DNA, which will lead eventually to apoptosis. Okay? Gemcitabine or gemcitabine or gemcitabine is an analog of cytarabine, okay? But it has fewer side effects if it's compared to cytarabine. Fludarabine, it is the purine analog. Cytarabine and gemcitabine are the pyrimidine analogs. The fludarabine is the purine analog. And you know what are the purine and the pyrimidine bases, right? Fludarabine has the same mechanism of action, but fludarabine it also inhibits transcription, okay? Which means fludarabine can also inhibit not only DNA polymerases but also the RNA, because it inhibits transcription. Well, cytarabine also may inhibit transcription as well. You can see here, these are the structures of the cytarabine, the triphosphate cytarabine, which is the active, and we also call it the ARICTP, the gemcitabine, which is the analog of cytarabine. The only difference between gemcitabine and cytarabine is those two fluorine atoms, and the gem name comes from these two fluorine are the same carbon. These are gem analog. Okay. This is the fludarabine. You can see this is a purine, and these are pyrimidine. I think now you know what do we mean when we say pyrimidine and purine. Okay. Other examples of inhibitors are the purine antagonists. Okay, these are prodrugs, just like the other ones. These, like the 6-mercaptopurine and the 6-thio or thioguanine, these are prodrugs converted to their corresponding nucleoside monophosphate by cellular enzyme. Okay? The monophosphate will inhibit purine synthesis. Okay, so first, these are prodrugs converted to the monophosphate. The monophosphate will inhibit purine synthesis. But they are also incorporated into DNA after they got converted from the monophosphate to the diphosphate, then to the triphosphate, as you can see here in the figure. Both of these, the 6-mercaptochlorine and the 6-thioguanine, will be converted to thio-GTP. And the thio-GTP will be converted to thio-deoxy-GTP. Deoxy means it's going to lose this hydroxyl group. Okay? Then the thio-GTP will be incorporated into RNA, and the thio-deoxy-GTP will be incorporated into DNA, and that will lead to the formation, either the chain termination or the formation of unfunctional or non-functional DNA, which will lead to apoptosis eventually. Okay? And again, if you have any question, just submit your question as a comment in Google Classroom. All right? This is the end of part 2. It's just a short part, and we will continue with the last part from this lecture, part 3. See ya in a minute.